Hello viewers, Wagdaruna taking you through the story for A-Level Physics Paper 2, and today we are going to look at arrangement of resistors in a circuit. So this topic is under current electricity and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline for this paper. Now, Physics Paper 2 is divided into 4 parts. The first part is Geometrical Optics, where 2 questions come from these topics and the student must answer one. Next is Physical Optics, or what we call waves, where 2 questions come from these topics and the student must answer one. Then the third one is Electrostatics and Electricity, where 3 questions come from these topics. And another one is magnetism and alternating current, where 3 questions come from these topics. So here it is up to you. You can choose to get 2 from here and 1 from here to make the 5 questions, or you choose 1 from here and 2 from here to still make the 5 questions which are needed in a complete paper. So here we looked at electrostatics, then capacitors, and now we are on current electricity. So in current electricity consists of these topics. One is the calculations, and in these subtopics, one is arrangement of resistors in circuits, then potential divider rule in circuits, resistivity and temperature coefficient of resistance, EMF and internal resistance of a cell, electrical energy and power, efficiency of a circuit, Kirchhoff's laws, Wheatstone bridge, meter bridge, EMF of a cell using a potentiometer, that is now measurement of internal resistance using a potentiometer, then also calibration of an ammeter and a voltmeter using a potentiometer, measurement of resistance of a cell using a potentiometer, and lastly measurement of EMF of a thermocouple using a potentiometer. So all these topics will be looked at bit by bit. So today we are going to start with arrangement of resistors in circuits. But complete notes on direct current current electricity are in this book called Mastering A-Level Physics Part 2. So it has notes, worked examples, and try questions on all these parts of Physics Paper 2. But our interest on this YouTube channel is worked examples. Then other books written by the same author are as follows. So if you are doing physics, then you need 3 books. You need Mastering A-Level Physics Paper 1, which is that, Mastering A-Level Physics Paper 2, and a Physics Topical Question Bank. If you are doing Principal Mathematics, you need Mastering A-Level Mathematics Paper 1, A-Level Mathematics Paper 2, and a Topical Question Bank. If you are doing subsidiary math, you need only 1 book, and that is Mastering A-Level Subsidiary Mathematics Paper 1. So sub-math has only 1 paper, and that is Paper 1. The rest are O-Level. There is O-Level Physics here and O-Level Math here. So now we can start our topic. So direct current electricity, or we can call it DC. So this direct current can be abbreviated as DC. So current electricity refers to the rate of flow of charge. So rate of flow of charge is current electricity. And in metals, it is the electrons. So metals have free electrons, so they're the ones which flow. Remember, charge can be positive or negative. So in metals, there are electrons which are negatively charged, which flow through the conductor. So what does that mean? It means that if a steady means direct current. So if a steady current, I, which is measured in amperes, flows for a time t, which is measured in seconds, the quantity of charge, capital Q, which is measured in coulombs, will be given by this formula, that Q is equal to IT. So sometimes they can give you the current and the time, then they want you to measure the quantity of charge. Or they can give you quantity of charge and time, then you want you to measure to calculate the current. So you remember to use that formula. There are some terms which will be frequently used in this video and the preceding videos under electricity. So we shall look at some of them. One is current density. So current density is the amount of current passing through a section of a conductor of cross-section area 1 meter squared. So the cross-section area must be 1 meter squared. We shall see how to derive this current density and how to calculate it in the next slide. So next is potential difference, and this is the work done to transfer a positive charge of 1 coulomb from one point to another in an electrical circuit. So know that the charge has to be positive 1. The charge has to be positive 1. The next is volt. So volt, first of all, volt is the SI unit of potential difference. Now what is a volt? Volt is the PD between 2 points if the amount of work done to transfer a positive charge of 1 coulomb from one point to another is 1 joule. And that volt is the SI unit of potential difference. So PD is an abbreviation of potential difference. Then we shall also look at resistance. So resistance of a conductor is the ratio of the potential difference of the conductor to current flowing through it. So you can say ratio, or you can give it in terms of ratio, or you can give it in terms of opposition to flow of current in a circuit. So next is ohm. Ohm is the SI unit of resistance. So an ohm is the resistance of a conductor through which a current of 1 ampere is flowing when the PD is 1 volt. So current has to be 1 ampere and PD has to be 1 volt. So those are some of the definitions which we shall look at in this video. So now we shall go to what we call drift velocity of electrons. Remember, we said in metals they are free electrons which are moving. So now what we want to look at is that drift velocity, the velocity with which they move randomly. So consider a portion of a conductor of length L and cross-section area A having n free electrons per unit volume, and each carrying a charge E. So E is a symbol to mean electronic charge. Therefore, shall try to draw a diagram to illustrate that. So it's a conductor of length L and these are electrons. So when you apply a current in this direction, it implies that charge has to move in the opposite direction. So when charge is moving to the right, electrons must move to the left. If there's no current, then they are free electrons able to move anywhere. But when there's current, the direction matters. If current is moving to the right, charges will move to the left. And if current is moving to the left, charges will move to the right. That is why you are seeing all the electrons moving to the left, because current is moving to the right. current is moving to the right and electrons are moving to the left. So this A is the cross-section area of a wire. So this is a wire, only that I've just magnified it in order to get an expression for drift velocity. So if this is the cross-section area and this is the length, it implies that if I want to get volume of the portion of the conductor of this portion, I will say area times length. So I've got volume. What about total number of electrons? Remember we said N is the number of free electrons per unit volume. Meaning that if I want to get the total number of electrons, I'll multiply this N times the volume to give you NaL. Then total charge is Ne. Is Ne, where N is the number of electrons times the electronic charge on each electron. So each electron has a charge of E. But how many electrons are they? They are NaL electrons. So I have to multiply this NaL times the charge on each electron to get the total charge. So now that I've got Q, I will come and say that if I is the steady current through the conductor, then I is equal to Q over T. Remember we said Q is IT. Therefore, when I make I the subject, I'll come up with Q over T. But I've already got that Q is NaLe. So I'll come and substitute for Q. So from there, I'll come and say that if V is the average drift velocity of the portion of the conductor, it implies that V will be distance over time. Remember, it moves this distance in which time? In time t, as it was given. So that means that drift velocity is equal to distance over time, which is L over E or L over T. And realize that it is here, L over T. What does that mean? I'll come and substitute. So substituting for V gives you I equal to NaVe. So where there was L over T, I'll replace it with V. But remember, they want drift velocity, so I have to make V the subject. So I'll come up with V equal to I over NaE. So that is drift velocity. But remember, I also talked about current density. So current density is current over cross-section area, because we said area must be 1 meter cubed. So to achieve that, I have to get the current divided by the cross-section area. So if I want to make I over A the subject, I'll be able to get the expression of current density as this. This is current density and is equal to NVE. So when they ask for current density, it will be equal to NVE. And when they ask for drift velocity, it will be I over NaE. So with that, we shall go through this question. Question 1 says, a current of 4 ampere flowing in a conductor of cross-section area 0.2 centimeters squared, and number density this per meter cubed. Find the drift velocity of the electrons in the conductor. First of all, we shall know that this 4 ampere is I, and this one is the cross-section area, but it has to be converted to meters by multiplying by 10 to the power negative 4. Then the number density is small n, that is number of electrons per unit volume. So now that I know that, I can come and get my drift velocity which they want. So I is here, N was given, A is given. Now this E is a constant and it is given in your examinations under the table of constants. So it's a constant and is equal to 1.6 times 10 to the power negative 9. So always at the front, at the first page of your examination paper, there will be a list of table, or there will be a list of constants which can be used in physics. And this electronic charge is one of them. So when I use a calculator, I'll come up with this as the drift velocity. So that was brief introduction. Now we shall go to our main part, which is arrangement of resistors in a circuit. Now, just like we saw under capacitors, similarly resistors can also be arranged either in series or in parallel. So let's start with series arrangement of resistors. So a number of resistors are said to be in series if they are connected end to end so that the same current flows through them. So for resistors in series, it is same current flowing. Remember, for capacitors, it was same charge flowing. But now, we no longer talk about charge, we now talk about current. We now talk about current flowing. That is one condition. Another one is that the total PD across the resistors in series is the sum of the individual PDs. So to derive the expression, we shall first consider three resistors, R1, R2, and R3 connected in series as shown below. So we have to draw a circuit diagram. So this would be the battery or source of PD, and these are the resistors, R1, R2, and R3. So the direction of current matters. In this dry cell, the longer one is the one which is positive, and the shorter one is the one which is negative in polarity. Therefore, current flows from the positive through the resistors and back to the negative terminal. That is why you are seeing this current here. If you put that direction in this side, it will not be okay because it will be opposing the rules of polarity. So here, this R1 has a PD V1, R2 has a PD V2, and R3 has a PD V3 across them. And this one is the total, meaning that when I add this plus this plus this, I must be able to get V according to this statement. Then this current is the one going through this, and is the one going through this, and the one going through that. So same current but different PDs, as long as it is series. Now, because of that, what does that imply? It implies that total PD across the resistors in series is the sum of the individual PDs. Therefore, V is equal to V1 plus V2 plus V3. Now, from Ohm's law, I will know that V is equal to IR. Now, V, for V1, it means that it will be I current flowing through that R resistance, R1, times that resistor. Then V2 will be IR2, V3 will be IR3. So I is the same because same current flows through them. So when I substitute, I'll come up with V equal to IR1 plus IR2 plus IR3. Therefore, when I make I this factorize out I, I'll come up with this expression. Then I take I this side, it will become V over I. Now here we shall come and say that if R is the effective resistance of the system, it implies that from Ohm's law, V over I is equal to R, because V will be IR. So when I make R the subject, I'll come up with V over I. And also here I have V over I. So what does that mean? It means that when I substitute, I'll come up with R equal to R1 plus R2 plus R3. So that means that the total resistance is equal to the sum of the individual resistors. Now with that, we shall make a summary of what has transpired. So the summary says that when the resistors are in series, the following should be noted. One, we have already seen that current flowing through all the resistors is the same. Is the same as that flowing through one of the resistors. Then 2, we have also seen that total PD is equal to the sum of the individual PDs. And lastly is this one, that the total resistance is equal to the sum of the individual resistance of the resistors. So it is different from capacitors. For capacitors, here we are talking about reciprocals as long as the capacitors are in series. But in electricity, when the resistors are in series, we talk about the sum of individual resistors. So it is like vice versa. What about parallel arrangement? So for parallel arrangement, resistors are said to be in parallel if they are connected alongside each other such that PD across them is the same. So the condition for parallel arrangement is that PD must be the same. So this statement is very vital because it will be used a lot in the calculations. And this is because the amount of work done in moving a unit charge from one common point to another is the same irrespective of the path taken. So that's the reason why PD is the same for parallel arrangement. So just like we did for series, we shall also derive the expression for parallel arrangement of resistors. So this will be the source of PD, and those will be the resistors R1, R2, and R3. So what this statement means that if I move a charge now, because current is moving in this direction, charge will flow in this direction. So if I move a charge from B and I take this path up to this point, or I move the charge from B and I take this path up this point, or I take a charge from B and move through this path, all paths will give the same work done. And because they all give the same work done, it implies that potential difference will be the same across two common points. That means that PD across R1 is equal to PD across R2 and is equal to PD across R3. But when it comes to current when it reaches the junction, it must divide. So here it divides, one goes this side to meet this resistor, one goes this side through this resistor, another on this side through this resistor. So the current I from the source divides at junction A such that different currents I1, I2, R3 flow through the resistors R1, R2, and R3 respectively. So I1 flows through R1, I2 flows through R2, I3 flows through R3. So that means that total sum of individual currents is equal to the total current. Therefore, I1 is equal to I1 plus I2 plus I3. And you already saw that V is equal to I1 R1. V is I1 R1 because current is through R1 is I1. Therefore, when I make I1 the subject, it will be V over R1. I2 will be V over R2. I3 will be V over R3. So V is the same because we said PD is the same across parallel resistors. Now when I substitute, I'll come up with this statement and realize that V is common. So when I take V this side or divide throughout by V, I'll come up with this. So here I say that if R is the effective resistance, so effective means total effective resistance of the system, it implies that from Ohm's law, V over I is equal to R. Therefore, I'll come and substitute this to come up with 1 over R. And when I get the rest, and 1 over R, but I know that 1 over R is equal to I over V, and I over V is this. Therefore, when I bring this one here, I'll come up with 1 over R equal to this sum of the reciprocals. So like I told you, it is just vice versa for capacitors. Capacitors in parallel, it was sum of total of individual capacitors, and capacitors in series, it was reciprocal, sum of reciprocals. But when it comes to electricity, it is vice versa. For series, it is sum of individual resistors, and for parallel, it is in reciprocals of the resistors. So that is the difference between capacitors and resistors when you are dealing with calculations. So in summary, for resistors arranged connected in parallel, the following should be noted. One is the total current is equal to the sum of the individual currents. Then 2 is that PD across each resistor is the same. The next is that the effective resistance is less than the least individual resistance. So that means that if you calculate and your total resistance is more than the least individual resistance, it implies that there's a mistake in your calculations. The total resistance must be the smallest of all. Now we have a special case, just like it was under capacitors. So a special case is two resistors in parallel. For capacitors, the special case was two resistors in series. In electricity, the special case is two resistors in parallel. So for two resistors in parallel, it implies that we shall come and write 1 over R equal to 1 over R1 plus 1 over R2, where R is the effective resistance. So I'll come and get the LCM and then get the reciprocal to give you product over sum. So that is a special case that if two resistors are in parallel, you don't need to first go through these steps to get the total resistance. What you need to do is remember that total resistance is equal to product over sum of the two resistors. And that's what we shall be using in our calculations. So question 1 came from an edited part of UNEB 2009 paper 2 question 8b Roman 2. Now why am I putting the word edited? It is because in this question, this was the circuit in that question, but these are not the questions which were asked. So what I did, I modified these questions to suit what we have so far covered. So far, what we have learned is how to get the total resistance and also total current. That is why I edited this question to suit what we have so far covered. So this question will be again redone when its part comes. But for now, let's use the circuit to get these two questions. So when you see this word edited, it means I modified the question to meet what we have so far covered. So it says a network of resistors, these ones, are connected to a 12-volt DC supply of negligible internal resistance. So by now you don't know what this word means, but the good thing they said negligible. Negligible means it can be neglected. So that means that we are still safe even if you don't know it because it has been neglected. Someday we shall know what it means. So negligible internal resistance as shown in the figure below. So the circuit, these are the resistors, and they said calculate the effective resistance in the circuit. Effective means the total resistance of all these resistors. Then 2, calculate the total current flowing through the circuit. So the total current flowing through the circuit. Okay. So first of all, you need to know which resistors are in parallel and which one are in series. So here, remember current flows from positive terminal through all the resistors up to the negative terminal. So at this point, current divides. One goes this side, another one goes this side. Then at this point, current divides, one goes this side, one goes this side. Then when it goes this through that side, it will come and meet at this point. This and this will come and meet at this terminal, at the junction. So at that junction, they will combine and go through this resistor. Then here, it will not divide because there is another one coming from this side. So the one coming from this side will come, reach here, and they join to go back to the negative terminal. So how do you know where to start from when you're getting the effective resistance? You look for where the current last divided. Where the current last divided, that's where you start from. So if you look at this junction, it's divided, one on this side, another on this side. At this junction, it's divided, one on this side, one on this side. At this junction, it combined. Then also at this junction, it combined. Therefore, we're not interested at these ones where it combined. We are interested at where it last divided, and that is this junction. And because current divided, it is known the same through this resistor and this resistor. What does that mean? When the current flowing through the resistors is different, it implies that the two resistors are in parallel. So the first thing to do is to combine this and this resistors which are in parallel. And the reason, you must know the reason is because this is where current last divided. Okay, so we shall come here and say that combining 2 ohm and 6 ohm resistors in parallel, we shall use the special case, which is product over sum, to give you 1.5 ohm. So after getting R1, it implies the circuit will be modified because these two will be combined. So these two will be combined into one resistor, which is 1.5. Now when that happens, still do the same. Look, the next step is to look at where current last divided. So here, current last divided here. But what does that mean? It means that these two resistors are in parallel with this. So for you to simplify your work, you must first combine these two resistors which are in series. When I combine, it means that I'll have to come up with this. So combining R1 and 1.5 ohm resistors in series, I'll come up with this. So I'll have to sum. So for the resistors in series, you sum the individual resistances to give you 3 ohm. So after getting R2, it implies that these two have been combined into one resistor, which is this. So now I can easily combine these two in parallel. So those two are in parallel, meaning that I will use special case of product over sum to get, and what I will get will be the total resistance in the circuit. So I'll come here and say that combining R2 and R3 in parallel, I'll come up with the effective resistance as product over sum to give you 1.5 ohms. And that's what they wanted in Roman 1. Now for Roman 2, they wanted the total current flowing through the circuit. Now total current means you have to get total PD and total resistance. Now the good thing, we know total PD, which is 12, and also total resistance, which is 1.5. Therefore total current will be total PD over total resistance to give you 8 ampere, and that will be the current they wanted. That was question 1. Then question 2 came from UNEB 2001, paper 2, question 8C, Roman 2, edited. So this word edited means the circuit is the same, but these writings have been modified to suit what we have so far covered. So a network of resistors, these ones are connected to a 6-volt DC supply of negligible internal resistance. Remember we said internal resistance, we don't know it at this stage, but the good thing, it is negligible, meaning you have to neglect it. As shown in the figure below, calculate the effective resistance of the circuit and the total current flowing through the circuit. So here, still you do the same. Current flows through this and reaches this junction. It will split. One will go this side, another one will go this side, another one will go this side. At this junction, it will combine to go through this resistor and go back to the negative terminal. So current last divided at this point, meaning that these three resistors are in parallel. So we have to first combine those three resistors in parallel. Now because they are three, we cannot use the special case. We have to use the reciprocal. Therefore, we shall come and say that combining these three resistors in parallel, I'll use the knowledge of reciprocal, and so 1 over R1 is equal to 1 over 1 plus 1 over 3 plus 1 over 6. So using a calculator, the whole of this gives you 3 over 5, 3 over 2. Meaning that when I get the reciprocal, I'll come up with R1 equal to 2 over 3 ohms. After getting R1, it means that now the circuit will be modified to this state, where all the three resistors which were here have been combined into one resistor. And when that is done, you will realize that the current flowing through R1 is the same current flowing through 4.4 ohm. What does that mean? It means that those two resistors are in series. Therefore, we'll come and get the total resistance by combining those two resistors in series. So I have to sum them up to give you this. But in physics, we don't allow final answers in fractions, so we have to get it in decimal. Here, it was allowed to leave it in fraction because this is not what they asked. The question asked for effective resistance. Now, what does that mean? It means that if this answer is left in fraction form, it means that the final mark will be denied. So always remember, in physics, we don't leave final answers in fraction form. It is in math where final answers are preferred to be left in fraction form. But in physics, final answers must be expressed as decimals. Of course, with an SI unit. Okay, now Roman 2, they ask for total current, so I know total resistance, this or this, and I also know total PD, so I'll come and get my total current from total PD over total resistance to give you this. Then question 3 came from UNEB of November 1998, part 2, question 8. Still it is edited, meaning that this circuit is the same in that year, but these words were modified to suit what we have so far covered. Remember, we have not covered much. So a network of 5 resistors, each of 6 ohms, is connected to a 50-volt DC supply of negligible internal resistance. So internal resistance, so far we take it to be negligible or neglected. After some time, we shall see what it means and how it affects the calculations. So calculate Roman 1, the effective resistance in the circuit, and Roman 2, the current flowing through the circuit. So still here, like I said, for you to know where to start from, you must look at where current last divided. So current moved from the positive terminal, reached F, it divided. One went this side, another one went this side. When it reached E, it also divided. One went this side, and another one went this side. So at this junction, it combined. and it went through this 6 ohm resistor back to the negative terminal. So where did the current last divide? Current last divided at junction E. What does that mean? It means that at junction E, we shall first consider this and this, which will be in parallel. So we shall come to our calculations and say that combining RBE and RCD in parallel. Now, what is RBE and RCE? Now, sorry, CD. So RBE is this one, because this is B and this is E, and RCD is this one. So when you hear me say RCD, it means this resistor, and RBE, it means this resistor. So I'm going to combine those two. When I combine the two, because they're in parallel and there are two, we shall use the special case of product over sum to come up with 3 ohm as the effect combined resistance of these two resistors. Now when I combine the two, I'll come up with this, because that means that the resistors which were here have been combined into one resistor, and that is a 3 ohm resistor. From there, we shall still look for where current last divided at F. It divides, one goes this side, another one goes this side. So what does that mean? It means that when I combine these two resistors, they will be in parallel with this. So to simplify things, you have to first get these two resistors in series. So let's first do that. So combining those two resistors, I'll come up with this. So add the two to come up with 9 ohm. And when I combine the circuit, now it was initially this, now it will become this. Remember, these ones have been combined to one resistor, and that is this resistor. So still I'll move my current from here to this point. It divides, one goes this side and one goes this side. Then here it combines to go back to the source. So that means that the next step is to combine these two resistors which are in parallel. So I come and combine those two resistors in parallel, which is product over sum, to give you 3.6 ohms. Now when I combine, it was like this. Now these two have been combined into one resistor, so to give me this. When it gives me this, you realize that the same current through this is the same current through this, meaning that those two resistors are in series. Therefore, I'll come and combine the two resistors in series to give me the effective resistance they wanted. So that was the effective resistance they wanted. Now we shall go to Roman 2, where they want the total current. So the good thing, we know total resistance and know the total PD, so we shall divide total PD divided by total resistance to give you 5.2083 amps as the total current they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on potential divider rule in electrical circuits. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.